Hi, I'm Samira. Welcome to session on OSPF. OSPF is Open Shortest Path First Protocol. It is an example of link state dynamic routing protocol. In this session, we will take a look at the concept of link state routing protocol. Then we'll move on to the features of OSPF. We'll take a look at what are the different types of areas and routers for OSPF. The types of packets used by OSPF in order to communicate between the two routers. The OSPF router states, that is, whenever you configure OSPF on router, what are the various states that the router will go through before it is converged. So that is all that we would be covering in this session. We will not be covering OSPF configurations in this session. If you are interested in understanding the configurations of OSPF, then please take a look at my video on OSPF configurations. In that video, I would be covering configuring OSPF for multi-area type of a topology using packet tracer. Let us move on with this session. We will begin by understanding the concept of link state routing protocol. Link state routing protocol uses something called as triggered updates. That is, each and every router present in the topology would flood the information about state of the links that are connected to it to every other router present in the topology. Hence, all of the routers would get information about every other router present in the topology and the links connected to those routers. Using this information, the routers can create the topology map, and this topology map is stored by the router in something called as a topology table. The protocols use shortest path first algorithm like the Dijkstra's algorithm on the topology map in order to derive the routing table. Also, if there is any change in state of link anywhere in the topology, the router to which the link is connected to will immediately detect this change and will immediately flood the information about the same to every other router present in the topology. This is what is called as triggered update. Due to the use of triggered update, the convergence in case of link state routing protocol is fast. This is as opposed to the periodic updates that take place in distance vector routing protocol, because of which the distance vector routing protocol have a slower convergence. Next, we will take a look at some of the features in OSPF. OSPF, being an example of link state routing protocol, makes use of triggered updates and hence has got fast conversions. OSPF uses Dijkstra's algorithm to calculate the best path from the topology map that is being stored in the topology table. OSPF supports large network. In case of OSPF, the network devices which are present in the topology are grouped into something called as areas. This is used in order to create a hierarchical design such that all of the routing updates within a single area can be summarized together and only the summary information can be sent to the neighboring area. This minimizes the routing update traffic in the OSPF network. This also speeds up conversions. In addition, grouping into areas also helps to restrict any network instability to that particular area only. OSPF supports VLSM. There are two versions of OSPF. OSPF version 2, which supports IPv4, and OSPF version 3, which supports IPv6. Both of these versions support VLSM. Let us take a look at what are the various types of databases or tables which are stored on OSPF routers. OSPF router stores three types of tables or databases with it. The adjacency database, also called as the neighbor table. This table contains a list of neighbor routers to which the router has established a bidirectional communication. That is, whenever you are going to configure OSPF on the routers would exchange some packets with each other and will try to form a neighbor relationship. If they are able to successfully create the neighbor relationship, they will put information about the neighbor router in the neighbor table. This table is unique for each router. If you want to view the neighbor table of the particular router, you can use the command show IP OSPF neighbor on that router. Next is the link state database or the topology table. The topology table contains the list of information about all of the routers in the network. So as we have discussed, while understanding the concept of link state routing protocol, the routers flood the information about the links to every other router present in the topology, and using this information, the routers are able to create the topology map. This information is what would be stored in the topology table. All of the routers present in the same area would have identical link state database. You can view the link state database using the command show IP OSPF database. Next is the forwarding database or the routing table. This contains the list of routes generated when the shortest path first algorithm is run on the topology or link state database. Each router present in the topology would have a unique routing table and would contain information about optimal path to reach any destination network. In order to view the routing table or forwarding database, you can use the command show IP route. Next, let us take a look at the different types of areas or router types present in case of OSPF. Whenever you are going to configure OSPF on the routers, you can create areas. Okay, so each area would have some routers which are called as internal routers. Okay, so this router in area 1, these are the internal routers for area 1. These routers which are present inside area 0 would be internal router for area 0. These routers present inside area 2 would be internal routers for area 2. You also have got routers which connect two different areas together. Such routers are called as area border routers. If you have got a router which connects multiple autonomous systems together, then you will call it as autonomous system boundary router. The routers which are present in the backbone area or in area 0 can be called as backbone routers. Okay, so a router can take on multiple roles depending upon what are the functions that are performed by the router. So in this case, this router which is present inside area 0, this is an internal router for area 0 and it is also a backbone router since it is present in the backbone area. In case of OSPF, we have got two different types of areas into which the entire topology is divided into: backbone area and standard or regular areas. The backbone area is a compulsory area and this is the area 0. Okay, so if you are going to configure OSPF on the routers within an autonomous system, then in that case it should have at least one area called area 0. If you want to create multiple areas, then one of the area is going to be the area 0 or backbone area, and the other areas would be standard or regular areas. Those areas can be area 1, area 2 and so on. All of the standard or regular areas need to be connected to the backbone area. They can either be directly connected or indirectly connected, but they need to have a connection with the backbone area. The backbone area is also called as the transit area because the information from the standard or regular areas would be sent to the backbone area, and the backbone area would send that information ahead to other areas. That is, area 1 will send information about routes within it. That is, the summary information will be sent to the area 0, and area 0 will send or forward that information to area 2, and hence area 0 is the transit area. The areas that are being created are created in such a way such that you can summarize the information of routes within a single area. In case of OSPF, the areas are formed in such a way that a hierarchical design is created. That is, all of the networks are combined into a single area such that the routing information within that area can be summarized, and only a summary route can be sent outside. In order to understand what you mean by route summarization, you can take a look at my video on IP addressing, which speaks about supernetting. Next, let us move on to understand the types of packets which are used by the OSPF routers. Whenever you configure OSPF on the routers, these routers are going to exchange some kind of advertisements with each other in order to form neighbor relationship and in order to exchange their link states so as to form the topology map. So the different types of packets that are being used by OSPF routers include the hello packet. The hello packet is used to discover the neighbors and build adjacency between them. So when you are going to configure OSPF on the routers, the first packet that will be sent by the routers is the hello packet. A router that receives the hello packet from its neighbor is going to check certain parameters in the hello packet. They would check parameters like the area ID, the subnet, and the hello as well as dead timers and so on. And they will check if these parameters match with its own parameters. If they match, then the router is going to reply with a reply hello message specifying that it is ready to become its neighbor. Next is a database description packet. The database description packet is used to check for database synchronization between the routers. Using the database description packet, the routers are going to send the topology table that they currently have to other routers. The neighboring routers are going to check their own link state databases and will check if there is some new information present in the database description packet. If there is some new information present in the database description packet, the router might want to update its own topology table. In order to do that, the router would need more information about that specific route which is not present in its own database. In that case, the router would send a link state request packet requesting for more information about a specific link from the other router. When a router receives a link state request message, it is going to reply back with more information about the specified link using the link state update packet. On receiving the link state update packet, the router will acknowledge with the link state acknowledgement packet. The link state acknowledgement packet is used to acknowledge certain types of packets like the database description packet and the link state update packet. Let us move on to understanding the various OSPF states. Whenever you configure OSPF on the routers are going to go through different states. Initially, all of the routers would be in the down state. So this is the first step of all of the routers. When OSPF is configured, the routers would start by sending a hello packet to the directly connected neighbors. Once the router sends a hello packet to its neighbor, it will transition to the init state. Okay, so if I have got two routers present and I configure OSPF on these two directly connected routers, then in that case, consider that router 1 first sends a hello packet to router 2. On receiving the hello packet, router 2 is going to check the parameters in the hello packet, whether they match with its own. If they match and the router 2 is ready to form a neighbor relationship, router 2 will reply back with a reply hello. When the router 1 receives a reply hello from router 2, router 1 will understand that router 2 is ready to become its neighbor, and router 1 will put the information about router 2 in its neighbor table and will transition to the two-way state. Once both the routers, router 1 and 2, enter into the two-way state, they need to start sending the database description packets to each other. In order to negotiate which router should send the database description first, they form a master-slave relationship. In order to negotiate the master-slave relationship, the routers would check the router ID. The router with a higher router ID will become the master, and the one with a lower router ID will become the slave. The master router is the one that will start sending the database description, and then the slave will send its database description to the master. The routers will check the database description packet. Okay, so once they have negotiated the master-slave relationship, they will enter into the start state. And then when they exchange the database description packets, they enter into the exchange state. The routers will check the database description packet with their own link state databases. If there is some new information present in the database description packet, the router might want more information about that route. And for that, the router is going to send a link state request message. Okay, so if they need more information, then they need to send more link state advertisements. To the link state request message, the other router which receives the link state request will reply back with a link state update. And this process will continue till both the routers or all of the routers present in the topology or within the same area have got the same link state database. Okay, so all of the routers within the same area should have an identical link state database. When that happens, we say that they have reached convergence, and that is when they will be entering into the full state. Okay, so these states will, the exchange state as well as more link state advertisement, this will keep on happening till the database reaches convergence. Okay, so once they have their database description same, they will reach the loading state, and once they acknowledge using the link state acknowledgement, they will reach full state. In the full state, the routers are synchronized with their neighbors, and the routers will start calculating their routing table by using shortest path first algorithm. In case of link state, or also in case of OSPF, which is a type of link state, Dijkstra's algorithm is the shortest path algorithm that is going to be used in order for calculation of the best route. Next, we'll take a look at DR and BGR. So in this example, in this OSPF states that we have seen. Here you can see that in the two-way state, there is an optional step wherein DR and BDR election would take place. So DR and BDR election will not happen always. It will happen only when you have got a multi-access broadcast type of a network, not otherwise. If you have got point-to-point type of a network, then in that case DR-BDR election does not happen. So you can take a look at these areas. Okay, so in area 0, for example, one router is connected to other router directly. So this type of connection is called a point-to-point link. And areas with point-to-point links are called point-to-point areas. Whereas you can take a look at area 1. Here I have got multiple routers which are connected to a common switch. Okay, so this is a multi-access type of area. Also, all of these are in the same broadcast domain, and hence this is a broadcast multi-access type of an area. In case where you have a broadcast multi-access type of an area, DR-BDR election will take place, and the DR-BDR election will happen when the routers reach the two-way state. Let us take a look at what is DR-BDR and why is it required. DR is designated router, BDR is backup designated router. These are used in order to reduce the amount of traffic in the network. So consider this example. Here we have area 1. In broadcast multi-access type of an area, initially when you configure OSPF on all of these routers, the routers are going to send hello packets in order to form adjacencies. Okay, so you can see the number of hello packets that will be exchanged. This router will exchange a hello with these 3 routers. Similarly, this router will exchange hellos with the other 3 routers. Okay, so that is going to cause a huge amount of traffic on the network. And each router will have neighbor relationship formed with every other router. Okay, so if I have these 1, 2, 3 and 4. My router 1 in its neighbor table will have information about 2, 3, 4. Okay, so these are neighbors for my router 1. Similarly, for my router 2, I have got 1, 3, 4 as the neighbors. Similarly for other routers. Okay, so each and every router will be sending the database description packet to every other router present in this network, and that is going to create a huge amount of traffic, and that is not desirable. And hence you are going to select one router amongst all of these, and all other routers are going to form neighbor relationship with only this router. So 2 and 3 will not form neighbor relationship with each other. 2 will form a neighbor relationship with 1, 3 will form a neighbor relationship with 1, and 4 will form a neighbor relationship with 1. The remaining routers do not form neighbor relationship with each other, and hence they will exchange the database description packet only with one router, not with each other. And this would help reduce the amount of traffic in the network. The router with which the neighbor relationship would be formed, this router will be called as DR, or designated router. You are going to have only one designated router in one broadcast multi-access type of an area. Now, if this router fails, you need to create some amount of redundancy, and hence you have got one more router which is elected as a BDR, which is backup designated router. The backup designated router will keep monitoring the DR if it is alive. If the DR goes down, then only the BDR will take the responsibility of DR, and then there will be a re-election for BDR. The remaining routers which are present in the area which are not DR or BDR would be called as DROther router. Okay, so if one is DR, two is BDR, then the remaining routers 3 and 4, these are DROther routers. Now let us try to understand how the election of DR and BDR take place. Initially, when the routers come up and then they detect that this is a broadcast multi-access type of an area, the routers understand that they need to elect a DR and BDR. First, a BDR would be elected. So the routers are going to check the priority of the routers. The priority of the router can range from 0 to 255. The router with the lowest priority, that is priority 0, would have the lowest potential of being elected as DR or BDR. Okay, so this router will probably never be elected as DR or BDR. The router with the highest priority has got the highest potential for being elected as DR and BDR. In case if the routers have got same priority, then in that case there will be a tie. The tie will be broken using something called as a router ID. So if I have got two routers, say 1 and 2, both of them have got same priority, then in that case, in order to know which router should become the DR or BDR, their router ID would be checked. The router with the highest router ID would then become the DR if their priorities are same. The default priority on all of the routers is 1, but this is configurable. You can change the priority. Okay, so first of all, the 4 routers which are present here, when they detect that they are present in a broadcast multi-access type of an area, they understand that they need to check the priorities. Consider that all of the routers have got the same priority, that is priority 1. Now in that case, the routers are going to check the router ID of all of the routers. One of the router would have the highest router ID. That router would first be selected as a BDR. Okay, so initially there would be only BDR present in this network and there is no DR. Now when BDR starts checking if DR is alive, the BDR will detect that there is no DR present. Then the BDR will promote itself to be the new DR, and then there would be an election for a new BDR. Okay, so first this one would have become the BDR. It detected that there is no DR present in the network, so it promoted itself to be the DR, and then amongst the remaining routers, they will again go in for checking the priority and router ID of them, and the one which has got the next highest priority or router ID will be the BDR. Let us try to understand what is router ID and how it is configured. In case of the routers that have got multiple connections to the multiple interfaces. Okay, so for example, this router that you can see here, this router has got 2 interfaces over which it has got connections. So there are going to be 2 different IP addresses on these 2 interfaces. The router does not have a single IP address. You do not have a single IP address. This router has got 2 IP addresses. So how can you have this router represented using a single IP? For that, you use something called as a router ID. You can explicitly configure router ID on the router using the router ID command. If you configure router ID on the router using the router ID command, that IP address would be taken as the router ID for that router. If the router ID is not explicitly configured on the router, then in that case, the router will check if there is some loopback interface configured on it. If there is a loopback interface being configured on the router, then in that case, the highest IP address configured on the loopback interfaces would be considered the router ID. Okay, so this router, for example, in order to know what is its router ID, the router is going to check if the router ID is configured using the router ID command. If it is not configured using the router ID command, the router will check if there is loopback configured. If you have multiple loopbacks configured on the router, then the router will check amongst these multiple loopbacks which are configured, which loopback has got the highest IP. That IP address would become the router ID of the router. If there are no loopbacks configured on the router, then in that case, the router would check what are the IP addresses configured on the interface connections. The highest configured IP address amongst the interfaces would then be the router ID. So with that, we have come to the end of the session. Thanks for watching. Please watch my next video to understand configurations of OSPF in a multi-area type of a topology or packet tracer. Also, please leave your comments. It would help me to create better videos for you.